With all the uncertainty in our day-to-day lives, wouldn't it be nice to know what to expect in the future? While we cannot completely predict the future, we can look at all possibilities and prepare for different scenarios. Using the computational tools we have today, we are able to estimate future stock prices, understand the dynamics of disease pathways to help treat illnesses, and even estimate your savings towards retirement when considering different economic scenarios. However, such computations require the use of running simulations, a process of computing hundreds, if not thousands, of scenarios to see what the most likely outcome of events are. An example of a simulation is the Monte Carlo simulation, and it is used in a large number of applications, such as climate studies, physics, engineering, finance, and even law. A simple example of a Monte Carlo simulation is throwing two dice. Suppose you want to know how likely it is to get a 7 as a result of throwing two dice, meaning if you get 1 in 6, 2 in 5, and so on, you will count it as a success. Rather than using complicated mathematics, we can estimate this probability by looking at this chart. The probability of getting a 7 is simply 1 over 6. However, Monte Carlo simulation requires us to actually throw two dice multiple times. For instance, you throw the dice 100 times and observe how many times 7 comes up. You will see that the result will be close to 1 over 6. If you do the simulation 1,000 times, then the result will eventually converge to 1 over 6. Now that we understand how a Monte Carlo simulation works, we can begin to explain the idea behind a nested Monte Carlo simulation. The nested simulation is different from an ordinary simulation in that we consider multiple layers including the inner loop and an outer loop. We often estimate quantities of interest with a range of outer loop scenarios over a period of time, during which additional quantities require further estimations from inner loop simulations. Let us explain these ideas with an example. Suppose we are trying to find the expected payoff from harvesting crops, based on the probability of the weather for the next 2 days. As a farmer, we are expecting harvest in 2 days and can only harvest crops when it's not raining outside. If the weather is sunny, we can harvest and make a profit of $1 per crop. If it is raining, we are not able to harvest and we make a profit of $0. Using historical weather data, we are able to find that the future weather is dependent on the current weather. We also know that it is currently sunny today. With this information, we can create a weather model for the next 2 days to calculate the expected payoff from harvesting. If it is sunny today, there is a 60% chance that it will also be sunny tomorrow, and a 40% chance that it will rain. The same probabilities would apply for day 2 as well, if it is sunny on day 1. However, if it rains on day 1, the chance of it being sunny tomorrow is 30%, and the chance of it raining again the next day is 70. In order to calculate the payoff we would expect to receive today, we must take into consideration all possibilities the weather can take for the next 2 days and assume the risk-free rate is 0. We can write the payoffs we will receive for each outcome as well, $1 if sunny at the end of 2 days and 0 otherwise. Using these probabilities, we can now run a simulation to get a sample of outcomes. We must run a simulation for both paths in our model. Let us start with the case of it being sunny tomorrow. The simulation runs a trial based off the probabilities in the model, giving us an idea of what we are expected to receive. In this case, we run 10 simulations to generate weather outcomes, resulting in 6 sunny days with a payoff of 1 and 4 rainy days with a payoff of 0, corresponding with our model. With this sample, we calculate the expected payoff we would receive by taking the average of all the payoffs in our simulation, resulting in an expected payoff of 0.6 or 60 cents per crop. We would do the same for the other path as well, running another simulation based off the probabilities of the other path. Running a simulation with these probabilities, we get a sample of 3 sunny days with a payoff of 1 and 7 rainy days with a payoff of 0. Taking the average once again, we get an expected payoff of 30 cents per crop for this path. The term used to describe the sunny path and the rainy path described by samples of simulations are called sample paths. In order to calculate the expected payoff today, we multiply the expected payoffs we calculated with the respective probabilities of each path occurring, resulting in an expected payoff of 48 cents per crop at time 0. In this example, we only ran the simulation 10 times to get a sample of 10. But in practice, we must run the simulation to get a much larger sample size in order to be accurate. Note further that we only had 2 sample paths representing sunny and rainy weather. In practice, we would need many sample paths representing a multitude of economic scenarios and run a large simulation for them as well, increasing the amount of calculations exponentially for each new sample path. In order to help reduce the amount of calculations needed, we can use the sample recycling method, which uses only one sample path to calculate the expected outcome of all possible alternative paths. To explain how sample recycling works, let us use the same example as before. In this method, we only use one sample from one path as a reference to calculate the expected outcomes of the other paths. Let us use the path that it will be sunny tomorrow as a reference to estimate the expected payoff of the path that it will rain tomorrow. We will refer to these paths as the reference and target paths. Next, let us find the expected payoff for each path, starting with the reference path. Running through the same process as before, we obtain a sample of 10 outcomes for the scenario that it will be sunny tomorrow. We get a sample of 6 sunny days with a payoff of 1 and 4 rainy days with a payoff of 0. Hence, we get an expected payoff of 0.6 for this path. Now we want to estimate the expected payoff for the target path. This time, instead of running another simulation to get a new sample, like what we did in the nested Monte Carlo method, we reused the sample of outcomes we had from the sunny scenario. In order to properly recycle this sample, we must find a relationship between the probabilities of the outcomes for the reference and for the target path. We can do this by taking the ratio of the probabilities for each path and each outcome. Let's first find the ratio of the probabilities for the outcome that it will be sunny. To do this, we take the target path probability of it being sunny and divide this by the reference path probability of it being sunny to get a ratio of 0.5, which we denote as lambda sun. We do the same for the probability that it will be rainy to get a ratio of 1.75, denoted as lambda rain. These ratios are what we call the weight, and we apply these to the respective outcomes in the reference sample. This adjusts the outcomes in our reference sample relative to the ratios between the reference and target path probabilities. A lambda sun of 0.5 means that the sunny outcome will occur half as many times in a hypothetical target sample than it will for our reference sample. Applying these ratios allows us to have a new sample that we can use for the target path to calculate its expected outcome without having to run another simulation. Using the outcomes in our sample, we multiply the lambda sun with the payoffs that we get if it is sunny. We do the same for the payoffs if it is rainy, using lambda rain for those outcomes. Summing up all the outcomes and taking the average, we get an expected payoff of 0.3 for the target path. Now that we have the 2 expected payoffs for each scenario, we can multiply the respective probabilities to get an expected payoff of 48 cents per crop, the same result as if we were to use the nested Monte Carlo method. As you can see, in this method, we did not have to run another simulation to calculate another sample to find an expected payoff. We simply use the same sample and relate the probabilities of each outcome in the sample instead, using the lambdas that we found. Again, in this example, we only had 2 paths, but in practice, we would need to have multiple in order to be accurate. Traditionally, with more scenarios requires more simulations to get a multitude of samples, but with the sample recycling method, we only require one sample, greatly reducing the amount of computation needed. As mentioned earlier in this video, Monte Carlo simulation is used heavily in other fields. In meteorology, weather forecasting often makes use of this technique to predict future atmospheric conditions. In telecommunication, wireless network design primarily depends on user data, such as their location and the services they wish to use. Again, due to the randomness of users, Monte Carlo simulation helps telecommunication companies plan their design. In finance, stock prices are uncertain, but one can estimate the cost of financial instruments whose prices depend on stock prices by running either a nested Monte Carlo simulation or using the sample recycling method. To see this process in more detail, be sure to check out our interactive webpage. To process uncertainty, many techniques can be done to draw a conclusion. Nested Monte Carlo simulation is accurate, but requires a large number of simulations to get a result. To be more efficient, the sample recycling method is introduced and can be applied to everything that is analyzed by nested Monte Carlo.